Today's lesson is lesson 2.3, and our topic is extrema and end behavior. Well, the word extreme is where we get this word extrema, and here we're talking about looking at a function and trying to identify the highest and the lowest point, relatively speaking. Now, most of these functions are going to go high forever, or they'll go low forever, or maybe both. But we want to know, relatively speaking, what is the highest point? Where can we find the highest point or the lowest point if they exist? And that's kind of in a nutshell where we're headed with extrema. And then end behavior, for a graph, on the extreme right side, where is the graph going? Is it going up or down forever? And on the left side, same thing. So just a quick snapshot of what we mean by these two topics. And so at the end of this lesson, and then especially after you've had a chance to practice some problems, I want you to be good at identifying what we call the end behavior, what happens on the right and the left sides of a graph as they continue, the numbers for x continue to get larger or smaller. And then can we identify what we call relative maximums or relative minimum points, and that's what we mean by extrema of functions. So I just have a few examples here. Some of your problems, they're going to be graphs of linear functions like these, and it's our job to describe the end behavior. Well, the right side, as you can tell, this line, typically lines go forever and ever in both directions. Well, here's how we'll state the end behavior of this particular linear function. And what we're interested in is, as we increase, let's just start with going on the right side, this right end, and as you travel right, you're increasing these values for x that we call the domain. So as you do that, then what happens to the values for y, or the function f of x? Well, let's state it like this. As the values for x approach, and we're going to use this little arrow to say approach, positive infinity. If you want to, you could put a plus sign there, but no sign at all indicates positive infinity. So as my values for the domain get increasingly larger, that's what this means, the function, and I'll just call it f of x, or you could have said y, means the same thing. Notice that the function, which is, notice y, the y-axis, those values are getting smaller and smaller and smaller. Okay? Can you see that? So as x approaches positive infinity, f of x is going to approach negative infinity. Okay, for the y-axis, the values on the y-axis, negative infinity is going this way. Okay, so we've taken care of the right end. Now let's go to the left. All right, so as x approaches negative infinity, so the numbers for x keep getting smaller and smaller and smaller. Do you notice that the function f of x, which corresponds to the values on the y-axis, well, those values are getting larger and larger and larger. So as x, the values for the domain, approach negative infinity, the function itself is approaching positive infinity. And it's okay, again, if you want to put plus signs for these, no problem. I would accept either way. So that would be a complete answer for letter A. Okay, let's take a look at letter B. As the values for x get larger and larger and larger, or in other words, as x approaches positive infinity, what happens to the function? Well, the function never changes. It's always that line. See, that's 6. It's the function f of x equals 6, or y equals 6. So the values for y never change regardless of what x becomes. If x is 4, y is 6. If x is 20, y is 6. If x is 160,000, y is still 6. So as x approaches positive infinity, the function remains constant. It's going to be 6. And that's also true for lesser values, or as x approaches negative infinity. Still the same thing. This is a constant function. Y, the y values, or the function value, will never change. It will still remain 6. So that would be my answer for letter B. Okay, now let's take a look at some nonlinear functions. Well, the idea is really the same. We want to know what happens as we increase values for x and as we decrease. What happens on the ends, the right end and the left end of this particular function. So if you want to, you can kind of split this down the middle, and let's start with as the values for x approach positive infinity. Okay, my inputs just keep getting bigger and bigger and bigger. Well, can you tell by the right side of this, the right end, where this function's going? It's going forever and ever to positive infinity. Okay, it's indicated the y-axis numbers are getting bigger as the inputs are getting bigger. Okay, outputs correspond to inputs in this case. And so let's see. We've taken care of the right end. Now let's do the left end. If we approach negative infinity with our inputs, what happens to the function, or where are the outputs going? Well, the function is still going in a positive direction. So the function is still approaching positive infinity regardless of whether I'm choosing bigger values for x or smaller values for x. The right ends, the end behavior is really the same. Okay, so that would be my final answer for letter A. Okay, letter B. Let's see, as we get bigger and bigger values for x, or as x approaches positive infinity, what's happening to the y values, or in other words, what's happening? Where's the function going? Well, as the numbers for x get bigger, looks like it's a gradual climb, but it looks like the values for y are also getting bigger. So we're going to state it this way: as the function, or as the inputs, the domain approaches positive infinity, the function will also approach positive infinity. Could put plus signs there, but it's not really necessary. Okay, well now let's go the other way. As we get smaller and smaller, or in other words, we're approaching negative infinity with our inputs, then what's happening to these y values, or where is the function going? Well, y this way is negative, and it's pointing in a forever negative direction. So in this case, as the inputs, or the x values, or the domain decreases, approaches negative infinity, that's also what the function is going to do. It's also going to approach negative infinity. Okay, so in this case we have they do basically the same thing. Positive creates a positive right end behavior. Negative creates a negative right side or right end behavior. Alright, so that's my answer for letter B. So maybe I can keep these straight this way. This is letter A. Now let's jump down to letter C. Well, as my numbers for x get bigger, so as x approaches positive infinity, do you notice the function, or the values for y, are getting smaller? Okay, so as my inputs get bigger, approaching positive infinity, the function is approaching negative infinity. And now we need to do the other side. As the values for x approach negative infinity, going this way, the function, or the values for y, are approaching positive infinity. Okay, y is traveling in an upward, the y values are traveling in an upward direction, which indicates positive infinity. All right, so that would be my final answer for letter C. So don't forget to do the right side, the right end behavior, and then also include the left end. Okay, so there's some examples, and now let's talk about extrema. And so a couple of keywords here. The first thing we're supposed to do is estimate zeros. I want to talk about what is a zero of a function, and then we're going to talk about these terms relative maximum or relative minimum. Okay, so first of all, what is a zero of a function? Well, another way of saying a zero of a function is an x-intercept. Okay, so you can either tell by the graph in this case. This table corresponds to this graph. So -3, -7, -3, -7 should be on my graph. -2, -2, there it is. -1, -3, that line's missing. It didn't copy over very well, but that's -1, -3. Here's 0, 2, and then 1, 25. We don't see the 25, but it's way up there. Okay, so the table and the graph go together. Let's first of all estimate the zeros. So another way of saying that is, can you tell, just estimating, where the x-intercept is? Well, I'm going to say since it's an estimate, I don't have to know exactly. I'm going to tell by the graph. I'm not told exactly in the table. If I were, a zero is where the function itself is equal to 0. Okay, so if they did tell me f of x equals 0 at a particular number, then I would know exactly. But they didn't tell me that, so I'm going to have to guesstimate. And the closest actual number, just think of integer, the closest integer to this x-intercept right here would actually be 0. All right, so it sounds kind of funny. We have a 0, which is just another way of saying an x-intercept, near 0. Sounds kind of weird, doesn't it? But that's actually the case. We don't have to know exactly. It looks like it's going to be a decimal. So don't get that exact. When you're guesstimating the zeros, you're looking at the closest to these actual integers on your x-axis. Okay, so that takes care of estimating the 0. We have a 0 near the, I'll just say near x equals 0. That'd be a little bit better. Let's say 0 near x equals 0. All right, x equals 0 is another way of saying the origin, and we're real close to that. It's closer to 0 than it is to -1. Okay, now let's talk about relative maxima and relative minima. And it's easier to determine those from a graph when you're given a graph. And these kind of make sense. Maxima means the highest point that we see. Minima means the lowest point. Now we can't really say an absolute maxima because, I mean, the absolute maxima is positive infinity, because this is going to go forever and ever upward. And the absolute minima would be negative infinity, because it's going to go forever and ever downward. That's why we use these terms relative, all right? The ones that we can actually see, these points indicated by this little hump right here, which would be the higher point, relatively speaking, and then this one down here, which would be the lower point, or the minimum. So here's how we state the final answer here. We have a relative maximum, and you can just abbreviate, at, and again, we're going to state it in terms of a number on the x-axis. So we have a relative maximum right here. That point is higher than this one. You see that? So I have a relative maximum at x equals -2. All right, and I have a relative minimum at x equals -1. So it's really just a matter of looking at the points on the graph and what is the highest point, relatively speaking. Again, the highest point's actually, there's no way absolutely that we could find it. But looking at this part of the graph that we can see, what is the highest point in terms of an x value on the x-axis, and what is the lowest point, just giving really the x part of the ordered pair. Okay, let's try another one. Let's estimate the zeros here, and once again, this vertical line did not come through very well, but there should be, just didn't copy, there should be a vertical line indicating x is -1. So when it says find the zero, that's just another way of saying, can you determine in an estimate where the zero is near? And we don't know for sure because it doesn't just say in the graph a 0 is where the function equals 0. Well, they didn't tell us where the function equals 0. So we're going to just estimate looking at the graph. And we have a 0 near x is -1. And again, 0 is just another way of thinking of x-intercept. Where is the graph crossing the x-axis? Okay. So I'll get that out of the way since you now know there's a missing graph line there. Alright, so we know where our 0 estimate is. Now let's look at relative maxima. So really we have these 2 points to consider. There's that point and that one. Obviously this one's higher. So the way we're going to state our relative maximum in terms of just the x-coordinate, that would be at x equals 0. Okay, officially it's you would say it's the point 0, 2, but we're just stating it in terms of the domain, or just the x-coordinate. And then we have a relative minimum at x equals 1. Okay, here's x equals 1, and there's the lower of these 2 points. So again, absolute, you'll get into absolute maximum and minimum later in higher level math. Well, this absolute maximum is positive infinity, and negative infinity would be the absolute minimum. But a relative max and min is just taking a snapshot of the graph where we can see the 2 points in this particular picture. Alright, let's see if we can do a couple more. Again, here's a table, here's a graph. They do not tell us a particular place where the function equals 0. So we're going to have to just look at the graph, which is pretty easy to tell. We have an x-intercept there, and this is an estimate. We don't have to try to come up with a decimal. It's closer to x equals 2 on the right side and x equals -2. So in this case we have 2 zeros. One at x equals -2, and then another one at x equals +2. Zeros synonymous with x-intercept. Where does the function equal 0? That's where it gets its name. Okay, now let's look for maxima and minima. Well, here are 2 of the lower points, and these would actually be considered absolute minima in this case. The absolute maxima would be positive infinity, because there's no way we could ever finish catching up to this graph that goes forever and up. But we do have a relative maximum. Okay, so we have these 3 points. As you can tell, the graph dips down to these 2 points. That's like the low level mark, and then it rises up here, not counting these that are absolutes, but this is considered a relative maximum. So we have a relative maximum at, again, just where is it in terms of x, and this is where x is 0. And we have relative minimums. actually 2. I'll just say relative mins at x equals positive 1 and x equals negative 1. Okay, here's negative 1 and here's positive 1. So we could just put them in order, I guess, going from left to right. Relative minimums, there's 2 of them. There is one relative maximum. It's the higher of these 3 points. And then we have 2 zeros because we cross the x-axis in 2 different places. Okay, let's jump over here to this one. Let's estimate the zeros. Let's see, where are we crossing? That's hard to see, but this is negative 3, negative 2, negative 1. It's very faint. But we have, looks like we have a 0 near negative 3. I'll do x equals, sorry about that. X is near x equals negative 3. Near x equals negative 1. Then jumping over here on the positive side, near x equals positive 1. And pretty close to x equals positive 3. Okay, and then since we have the graph, I think it's easy enough to tell, but you can also tell, let's just take negative 1 for instance. Do you see how our values for x jumped from a negative to a positive? Well, that always indicates that we have a 0 taking place in between here. And we don't know exactly, it's a decimal, but it's closer to negative 1 than it is negative 2. So these, whenever the signs change, if you're not looking at a graph, if all you had to go on was the table, you can always tell a 0 when you have a sign change from negative to positive. Alright, that happened here as well, positive to negative. So in other words, we jumped from above, if we're going from left to right, we went from above the x-axis and then we dipped below. In order to make that happen, you had to have crossed the x-axis, and that probably makes sense. Negative 3, 8.5 would be up here, negative 2, negative 4 is here. So to get from positive on the y to negative on the y, obviously you had to cross. So just want to give you a heads up, if we don't have a graph, then you can still tell where the approximate zeros are just by looking at sign changes. Notice here we went from positive to negative, and that's why we're listing positive 1 as a 0, because we had to have crossed over the x-axis in order to get from this point to this one, or vice versa. Okay, so we've listed all of our zeros approximately, and now let's think about relative maxima. Well, this point qualifies. It's the highest relative point that we see, and that's at x equals 0. Not writing very well. X equals 0. Okay, precisely it's the 0.04, but we're just going to state it in terms of the x values. And then we got these 2 here down at the bottom. They would be considered relative minimum, relative mins at x equals negative 2 and x equals positive 2. Okay, so there's a lot involved in this one. We're crossing the x-axis 4 times, so we have 4 zeros. We have one point that's higher than these other 2. It's a relative maximum. And then these 2 at the bottom are considered relative minimums. And that takes care of this problem. And so I hope that helps you with the assignment. And if there's anything about this you don't understand, come see me in academic support, or shoot me an email, or just bring your questions to class. Work hard on this and let me know if I can help.